Let's do another example of an application of Bernoulli's equation. So this application is a pitot tube. It's a device called a pitot tube where the objective is to measure the oncoming wind speed coming from far away from an object. So let's assume that there is a pressure far away from the object called P infinity, and the oncoming wind speed is V infinity. So this is a device that you might put, for example, in front of a commercial aircraft. So these generally are things that you find there. So the way that a pitot tube is constructed is that it's sort of a hollowed out material where there's a little tube that comes to the front side of this device that is exposed to directly, like in the normal direction, to the oncoming wind flow. And then there's another port that is mounted to the side that's open to the atmosphere, but at a perpendicular angle to the oncoming wind speed. And then what you do is internally inside the device, you sort of route those openings to some sort of pressure measurement device that measures the pressure difference between these two ports. So now there will be a pressure difference between the two ports because as long as air is not allowed to flow through from one port to the other port, this becomes a hydrostatic situation inside the device. And so at the front end of the object, you can trace a streamline where the fluid velocity has to go from V infinity and decelerates down to zero, a velocity of zero. So basically there's a stagnation point on the very front end of the pitot tube. But then on the side-mounted port, you don't have that case. So the fluid basically just flows right by that port. And so its fluid velocity is maintained at a speed V infinity as it goes around the side. All right, at that point, it's helpful to write Bernoulli's equation for those two streamlines that have been identified. So first let's do the one that goes to the stagnation point. So if I draw a streamline from infinity, or from point A going to point O, Bernoulli's equation would say that P infinity plus half rho V infinity squared plus whatever rho G times the height at that location should be equal to the pressure at the stagnation point plus half rho times V at the squared at the stagnation point plus rho G Z at the stagnation point. The two heights are the same, so the rho G Z's on both sides cancel. And in this case, because it's a stagnation point, we know that the velocity at point O, the stagnation point, is zero. And that allows us to figure out the pressure at the stagnation point, the same as we did in the first example. But then if we calculate the pressure at point B, so the port that's side-mounted, it's different because the velocity at point B is not zero, it's V infinity. So we can write out the same thing. So we can identify a different streamline starting from point C in this picture, where P infinity plus half rho V infinity squared plus rho G Z at point C is conserved along that streamline, and that equals the pressure at B plus half rho V times the velocity at B squared plus rho G Z evaluated at B. Again, because of the way I've selected these streamlines, the vertical velocity change is zero in this case, and thus that term cancels. And the velocity at B we think is pretty close to V infinity, and so that term cancels on both sides of the equation, and you find out that the pressure at point B is exactly the same as the pressure at infinity. So you can take the pressure, or you can calculate the pressure difference between the stagnation point and the side-mounted port, and you find that that's just equal to half rho V infinity squared, regardless of what the absolute pressures of the system are. And so you can solve that for the velocity, V, so as V infinity equals square root of 2 times the pressure difference divided by the density. So in practice, what you do is you just have to measure this pressure difference that occurs across those two ports which I think in the old days you would do this with a manometer. I think these days you'd probably do that with like a differential pressure transducer. But in either case, by measuring the pressure difference, you can measure, V infinity, the oncoming wind speed.